All right, we can go ahead and get started. Welcome to today's meeting on quantum computing. So a few quick announcements. Our scavenger hunt has been pushed back to April 15th. So we're going to have a new sign-up link. That's going to be on the Discord and the slides, access those. And we have a social next Thursday. I don't know much about that, but we have a social. Yay, you should come to that. And now we have our meeting flag. So I'll give you guys a moment to type that in. You know, the quiz, which is like the actual quantum org here at Illinois, they had a table set up at the premiere of Quantum Mania to basically tell people how all the science in the movie was bad. What's up?
I mean, it's a movie.
Yeah. He shrinking people down to the size of ants, and then it's like, I can't do that either.
You have to write on someone's parade. Right. Give it a second. All right, and that's going to be up there after the meeting. That's that. Okay. So before we start off, this is a disclaimer. I have no idea what I am talking about. Okay. If you're looking for like a rigorous quantum computing fiber, this is not it. The good news is I have some resources at the end for you, but yeah, this is like how to guess God CTF challenges that like you hope you can just intuit the answer. There are a few courses up here. I wrote down what each of these are. I'm kind of curious. Like as a show of hands, does anyone, if you've taken any of these classes up here, can you raise your hand? Hi. Yeah, you're at SIGPwny, so hi again. Okay, this means I can lie to my audience and no one will have any idea I'm lying. Sweet. Yeah, but basically, this is a fairly new category. This is like a new presentation we're doing this year. And even the challenges at like at a very high level are still somewhat, I guess you could say like easy comparatively. And by the way, if I say trivial, just completely ignore that. That's just that's a bad habit. But yeah, these are kind of hard. Quantum computing is difficult and like a paradigm shift from classical computing. So like, don't be afraid to ask for help. And of course, Google away, as you all are very good at by this point, I assume. Okay, so just to get started off, like, what is quantum computing? There's kind of like three things I want to go over initially. First is qubits. That's your unit of quantum information, quantum bit, right? I don't have a box up here. I had it on the original, like, oh wait, it's all in out page. Just hopefully you have like a little image of that. Basically, instead of being either a 0 or a 1, you can be in a superposition of like some amount of zeroness, some amount of oneness. And this is kind of like at a very fundamental level what helps quantum computers be faster and more special than classical computers. And instead of the imperative programming model, I'm sure you all are used to by now, we use something called a circuit model. Other models do exist, but this is the most common one, and in my opinion, the one that's most easy to reason about and work with. Where basically you apply circuits, and the circuits are all like under the hood just matrices. So it's all just linear algebra. I wasn't joking on the first slide. It's all linear algebra. For hardware, this is something we don't really worry about. There's a lot of very interesting things to see. You know, like this, like the big chandelier computers you may have seen pictures of. Those are superconducting quantum computers. But for our purposes, right, like no one actually has access. Like no one here actually has access to a quantum computer. And if you do, it's only like 7 qubits, and you can simulate that. I am going to go over simulators a little bit later and kind of like where that comes into play in quantum challenges. But for people kind of scratching their heads and being like, quantum computer, but I don't have a quantum computer. Well, you don't need one. You just need a classical computer and just hope that it's like good enough, right? Right. Okay. So what makes qubits special? So I talked about superposition a little bit before. It's having this amount of zeroness and oneness. And basically, one of the consequences of having a continuous range of values instead of just a discrete 0 and 1, you can literally encode an arbitrary amount of information, right? Although because of something called the measurement rule, you have to like in order to extract information out of your quantum system, you have to measure it, and by doing that, you destroy its state essentially. So if I measure in the computational basis, which is what we're going to be doing pretty much all the time, at least for CTF, you're going to collapse your state to a 0 or 1. So you lose your continuous value. And the only way you could reproduce that experimentally is by measuring a bunch of times and kind of hoping as you measure more and more values, you get it better and better. For certain challenges in CTF, which we're doing, instead of measuring values, you can do things like take your state vector or your density matrix. Some of these are a little bit beyond the scope of CTF, but the point is, it's not necessarily, oh, I have 5 qubits and therefore I'm going to get 5 qubits out. And this is actually going to appear in the challenges I have for you after the meeting. For entanglement, this is like the classical quantum computing thought experiment of Schrodinger's cat, which actually demonstrates superposition and entanglement. But just out of curiosity, has anyone here heard of Schrodinger's cat? Oh, awesome. Okay. What a lot of people don't know is that where you have like the cat in the box, it's like some amount of live, some amount of dead. Basically, the mechanism by which you kill the cat is poison, right? Because yay, PETA. But the idea is like you take this quantum event of a decaying particle, and you don't know what it is. It's in some superposition, but then through some setup, you're able to entangle its fate inextricably with that of the cat like eating the poison and dying. And when you open the box and if the cat's dead, well, what do you know about the particle? You know it decayed, right? And vice versa, if the cat is alive, you know the particle didn't decay, and if you know the particle decayed, the cat is dead, this, that, the other. And entanglement, like these two together, superposition and entanglement together, are what makes quantum computers really powerful. Interference is really just a natural consequence of superposition, but I bring it up here just because, and again, this is not rigorous in any way, but it's just like kind of what makes everything work out, right? Like you have, you're creating like a huge problem space, and well, the reality is you don't actually want all of your inputs. You want to find the input that gives you the right output, right? And so like constructive and destructive interference is how you amplify the stuff you want and get rid of the stuff you don't want. So this is how it all just kind of works out. Okay, this is like the last math slide, I promise. Something that's really, really, really important, including for CTF challenges, circuits and by extension gates. It's just matrix multiplication, right? You're not going to do that on paper, probably, unless I am really mean to you. But just unitary matrices, meaning they're invertible. You can reverse them, right? Take the inverse. And quantum computers in the circuit model, it's a model of reversible computing, and I'm going to get into some of the consequences of that later. In terms of notation, this is probably unfamiliar to most people, but this is something known as Bra-Ket notation. We actually only use, I mean, you could use the bras somewhere, but pretty much we only use the kets to get this 0 and 1. All you really need to know is that it represents the classical 0 and 1. If you're interested in learning more, it's just like this ket is like the n-dimensional vector where like the 0, that's like the 0th index is a 1. And in the case of qubits, because it can either be a 0 or a 1, just dimensionality too. The other thing is tensor notation. You can basically like smush 2 kets together to get a register of kets. So you can, like, it's just like a register of classical bits. The tensor notation gets abstracted away, so don't really worry about that. But if you see something like this, where you have like a superscript tensor product, and that just means like your quantum register is n qubits long. Yeah, and so circuit diagrams. Typically, you'll see one of 2 things. It depends on the challenge. Of course, in CTF, it's going to be over your terminal, most likely. And so you're going to see something like we have on the bottom, where it's like box draw ASCII art. Up top, that's like a LaTeX meme you might find in a paper. And trust me, like a lot of these challenges are just guess the paper, so you will be doing some reading. So at the start, you start off with typically your 0. It doesn't necessarily have to be that, but just by convention, that's what it is. You start off with your 0, and then your gates are these little boxes, and the letter on the box just tells you like what operation you're doing. So for example, this is a RY, that's a rotation around the y-axis by some arbitrary amount. HAL, this is a fake gate I made up. This is taken from one of my papers, but don't worry about that. And then these lines here with these black, and you don't see the white dots, but the black dots is something called a control gate. And I'm going to get into what that is a little bit later on, but you can think of it as like a super powered if statement of the quantum realm. And then finally, on the right side, we have measurement operators. And this is one of the ways where you can extract state out of your quantum system. Okay, great. So useful gates is on the next slide. So here's kind of interesting. Getting back to why it's all just linear algebra, you really only need a very relatively small set of basis gates, and that provides this concept of universality, where you can basically do any quantum computation. And for those of you who are like might be thinking any computation, yes, this includes classical computation. So quantum computers are Turing complete. I guess also the other way around, because you can simulate a quantum computer. Typically, the base gates idea is abstracted away. Like you take your quantum circuit and you will transpile it to some platform, or you'll optimize it, or something like that. What's up? Yeah, exactly. And yeah, so you can simulate a quantum machine. Now, depending on what your quantum machine looks like, that could be like really, really, really bad, like 2 to the n bad or C to the n bad. And so like you don't act like, there's a reason we haven't been able to just use Shor's algorithm on our computers. And if we could, I sure hope we didn't do anything sketchy on the internet today. Yeah, but good question. There's a set of useful basis gates. The one, this R, X, Y, Z. Again, getting back to this like block square idea, we have our qubit and our classical zeros at the North Pole and our classical ones at the South Pole. We can just do arbitrary rotations around there. And again, amount of zeroness and oneness. If you have 0 at the North Pole and 1 at the South Pole, being on the equator means you have an equal amount of zeroness and oneness. You're in a superposition. And you get anywhere on the sphere with this Rx, Ry, and Rz. Another one that's really, I wouldn't say popular, it's not like it's a popularity contest, but really useful is Hadamard. And that will map this classical 0 and classical 1 to an even superposition of 0 and 1. You see that all the time. And yeah, so control gates. So again, linear algebra is great. It makes our life very useful. So we can control any gate we want, because again, they all like compile down to the same thing. There's not, I don't really have like a better, more rigorous explanation than that. And control gates is how you actually get entanglement. I'll show you the most simple example of entanglement a little later on in Bell state. But like controlling gates on 2 qubits, that's how you actually like link those qubits together, you can think of. Okay, now this is like a little bit deviating from, actually no, I promise this is on topic, but this is why people are excited about quantum algorithms. So there's 3 main applications. The first one being the Fourier transform. And this is like, ooh, you know, like our super polynomial speed up from 2 to the n to n squared. This is a huge component in a lot of the really big, I guess, like killer algorithms and applications, including Shor's algorithm, which I'll get into that a little bit later. But like this is what makes quantum computers really exciting, because it's huge speed up. We have search algorithms, which is like, you know, you can query a black box, and essentially you're able to do it in fewer queries on a quantum computer than you could do classically. You can also get a speed up that is like not quite as good, so people are a little bit less hyped about it. And then simulation is also like very interesting for medicine and chemistry, but that doesn't have any applications to CTF, so we're just going to ignore it.
I have a question.
Oh yeah.
What does simulation mean exactly?
Yeah, it's a great question. So Richard Feynman, when he originally proposed the idea of quantum computers, it wasn't so much, you know, well, we're going to have like gates and we're going to do our algorithms and stuff, but to have a model of quantum systems, because, you know, let's say you're trying to fold proteins or do things at a very small level that, if you want to simulate a quantum system, it's very hard to do that classically, because, you know, as you add more and more qubits in state, that grows exponentially. And so one of the ways that you can simulate that efficiently is like using a quantum computer to simulate a quantum system. It's just kind of inherently good at that. And it's less so about using the gates, I guess you could say, and it's more so about just there are quantum particles that you can control to do things, and that makes it better than like classical bits, right? Any other questions? Awesome. So there's a bunch of caveats, like the quantum speedup, it's a big fat asterisk in the right-hand corner. There's a few things. Number one, like a no order of, like not really no order of importance, but no cloning theorem. You cannot take a qubit and like perfectly copy its state. You can perfectly copy its state, but you can't perfectly copy its state. You can move qubits, you can teleport qubits, but you cannot clone a qubit. This actually has some interesting applications in prior CTF challenges. I'm not going to go into it in this meeting, but like it may be a thing in the future for future CTF challenges. No teleportation theorem. When people talk about like no spooky action at a distance, like the first thing they think of is like, wow, we can send information faster than the speed of light. And physics says, no, you can't. And so with qubits, I was talking a little bit earlier about how our quantum computers are reversible. I don't know, if you're like me and you're kind of a bad and lazy programmer, like you're going to rewrite things, like you're just going to discard state they don't actually need when you're programming classically. You can't really do that on a quantum computer because that's irreversible. And so qubits are used everywhere in quantum computing, and technically also classical reverse computing, but that's not really as well researched of a field, I suppose you'd say. Hardware is fickle. Again, we don't really care about this because we're doing simulator stuff. But in terms of like, why is the height, like, why can't I break into my neighbor's computer? The reason is quantum computers are not that big, even though they are big. They're very, very, very fickle. So like decoherence, like the gates we have, like it's all nice and good to rotate on the Bloch sphere, but like, can we really get like exactly a rotation of pi over 6 radians? It's very difficult to do that. So there's always some error, and that error quickly masses up and becomes a problem. And so for that, we have error correction. And it's a little bit more complicated than classical error correction, as you would imagine. We're not really going to go into that here because not that many applications in CTF, but it's a very, very interesting field. And if you were able to like find one of the answers to the open error correction problems, I'm sure people would hire you. I'm sure you'd make a lot of money. Okay, now the thing everyone has been waiting for, or maybe not, because I didn't announce it at the beginning, but now you can like build your anticipation. Is Qiskit, and this is like quantum home tools, right? Like just use this. A little bit of interlude. This was not part of the presentation, but me last night having to rewrite everything I wrote in a different quantum framework. I was like, oh, you know, a little naive. Oh, I'll write it in Penny Lane. Things will be great. Things were not great. Things were terrible. Okay. So sorry, and I'm kind of like dunking on this other quantum framework. They're all pretty great. Some have their advantages and disadvantages. But the one that's kind of the most matured is something called Qiskit. The pronunciation of this is like actually a joke. There is no right way to pronounce it, just so you know. But yeah, so you can install that for Python, and this is how you actually code quantum computers and make your quantum circuits. As for the actual CTF challenge, I guess challenge cycle, how you want to be going about solving your challenges, just how like you open up Chrome DevTools when you're solving a web challenge. There's kind of this stage for intuiting like what the solution to your challenge is. And generally, you're gonna get some circuit, or you're gonna be able to apply some circuit. You're gonna apply your gates, simulate it, whether it's on the server or on your own computer, and then you're gonna do some sort of post-processing classically with your output. And I can put this back up later. People need to install that to work on the challenges. But yeah, it's like pip install Qiskit. Okay, so here is what you could consider to be the quantum equivalent of Hello World. And this is the Bell state. So this is how you get the simplest like non-trivial entanglement. And so I know I discussed it a little bit earlier. Also, all these gates are going to have one-letter names. It's going to be very confusing at first, but you'll be used to it soon, I promise. This is the Hadamard gate, which again gets us to this even superposition. So now qubit 0 is kind of 50% 0, 50% 1, and it could collapse to either with the same probability. And then we do this controlled NOT gate. And essentially, well, what do we do a control on if it's not 0 or 1? It's a combination of both, right? And so consequently, this Q1 also becomes a combination of both. And it becomes linked to Q0. So we measure Q1, we know Q0, and vice versa. In terms of actually the code, This is kind of bad practice, but just wildcard import, just like cone tools. You create your quantum circuits. There's also like quantum registers and classical registers. It abstracts that away from you. If you just do quantum circuit, this 2 is like the number of qubits. And then you just have like the most common gates you would apply are just methods. So you use circ.h and then on the qubit. And then circ.cx, which is controlled x. And you'll notice that anytime there's a controlled gate, it's going to be C and then the name of the gate. And then it's your control qubit and it's the target qubit. And then you measure all and you're done. And everyone's gonna. All right. Does anyone have any questions about this? You don't need to code this, but like this is just a very simple example of like how you might go about using Qiskit. Yeah.
So when I'm running measure all, you mentioned that like the Hadamard, if I'm saying that right, has an equal probability. So I could measure either a 0 or a 1 for measure all. What is the output of measure all?
Yes. So that's a good question. The kind of missing piece of the code that we don't have here is we haven't actually run the circuit yet. We just have a circuit. We basically just have a big fat matrix, and we haven't done anything with it yet. Measure all is just a convenience. It applies the measurement gate to all of your active qubits. So in this case, Q0 and Q1, and we're going to measure them, and it's going to output like some classical bit, right? So in the event that you have Q0 and Q1 are in this, it's called a Bell state, which is like the simplest entangled state. Q0 is either going to be a 0 or a 1 because you're measuring along the z-axis. That's not really important, but you're going to measure either a 0 or either a 1.
I see. So yeah, they can be 0 and 1 and 1 and 0 because of the NOT gate, but you don't know which yet.
It's either 0, 0 or 1, 1.
Wait,
Yes, sorry.
it says 0, 1 there, so you're 0, 1, and 1.
Oh, sorry. Yeah, this is like a weird thing with like matplotlib. This just references qubit 0 and that references qubit 1. Typically what you'll see is you don't really care about like the classical register because all you're doing is measuring to it. You're not really performing any calculations on it during the quantum circuit. So you'll like this just means like I have 2 classical bits and I'm like bundling them together.
Since it's not the, why do they not just go 0, 0, 1, 0, 1 instead of opposite?
Yeah, that's a really good question. You can kind of think of it as, I would say, I have an example a few slides from now. It's kind of like an XOR, I guess you could say, in this example. Right, like you know how you can kind of like, because you have 2 strings for XOR, and how it's a 0, like 0 XOR some quantity, it'll do nothing, right? But if it's 1, it'll flip the bits. It's kind of like that here. So you could like, okay, this is not a generally good practice to think about it, but because it's not like imperative. Like you don't go, oh, I measure the Hadamard and then I do the control. It all happens at once, and they're just linked. But you could think of it as like, okay, the Hadamard 50% 0, 50% 1. If it's a 1, then this control is going to activate, and this is a 0, and now I'm going to flip it to a 1. So now I have 1, 1. And if it's a 0, this control is not going to activate. It's not going to happen. And so I have 0, and this was 0 from the beginning, so I have 0, 0.
Okay. I misunderstood what the control thing was.
Yeah. Sorry about that.
So you're saying that if it's.
Sorry. Did you have a question?
I did. I was like, is this value decided at runtime?
Yes. So whenever you run this circuit, and again, like on a real quantum computer, this Hadamard gate is imperfect. This control gate is imperfect. Even your measurements are imperfect. Like the time it takes, your qubit can decohere. So you might not actually get exactly 50-50, but like if I ran this circuit many, many times, I would on average get like 0, 0 half, like 50% of the time, and 1, 1, 50% of the time.
Are there like convergence to be expected from it?
Yes, I mean, with a quantum computer with like real noise, you're technically not getting this 50%, so it wouldn't necessarily converge, but like generally speaking, yes. And also on a classical simulator where you can choose the noise profile, and generally you don't want there to be any noise, yeah, it would just be 50-50. But it's a probabilistic measurement, so I couldn't say for sure what it would be if I measured it. Like if you plot a histogram, it'd be like about 50-50.
So I guess then, like, sometimes when you're making quantum circuits, I guess you have to like account for both control paths and both the possible values.
Yeah, and a lot of the time, because so like I run it like it's like an if statement, and it's a little bit more than that, because it's not like, oh, if one thing, then do this and then execute this path, or like branch. It's really more so like you're packaging these qubits together, and they're best friends forever. You know, like they right, Q0 and Q1, they're totally inseparable. I mean, I know you could separate them again. That's another story. But yeah, it's, you know, if Q0 is going to be 0, Q1 also has to be 0.
But then it's like a dependent. So like,
Yeah.
You could actually depend on something.
So if subsequent things happen to Q0, move to in way after the gate established, then Q1 follows it.
Yes, that's an excellent question. Yeah, so these qubits are, until you like unentangle them, do something to unentangle them. Yeah, they're best buddies, right? So if you do something on Q0, the same thing is going to happen. Well, not like necessarily the same thing, but that would be reflected in Q1. So if you, for instance, if you were to apply a NOT gate on Q0 after this control, again, like, lazy way to think about it. Okay, this is a 0, and then it's a 0. This is a 0, and then I apply a NOT gate, so it's 1. So now it's 1 0 or 0 1. But you see how like they're still related, right? So you changed, like me applying a NOT gate here doesn't change it, but like the relationship between 0 1 1 0 hasn't changed. That's not a very convincing explanation, I know. Yeah. Did that kind of answer your question, or?
Sort of. So Q1 state is not like update, so it's always equal to Q0, but it is always related to Q0.
Yes. Yeah. So even though you can like do further operations on Q0, if you have information about it, you collapse it and you measure that. Now you have information about Q1 too. Yeah.
Oh, so that's what you mean by reversibility.
Yes. So, and again, everything here, so like excluding this Hadamard gate, this 2x2 matrix, and this control gate is just a 4x4 matrix, and they're all invertible. So you can take inverses, and you can just work backwards. Actually, there is that does come up later in the challenges. So keep that in mind. Yeah. Any more questions?
So does like what happens to the state of Q1 has like a value before the controlled NOT gate?
Yeah, another good question. By convention, we start off at the cat 0, which is the classical 0. That's our like initialized state.
Gotcha.
You don't necessarily have to do that, but that's just convention.
And then my other question is like more complicated, but so you've applied like the controlled NOT between 0 and 1. What would happen if you like added a line of code that after you did the control NOT 0 1, you do control NOT 1 0? Like, right, then they're like dependent on each other in a sense. Is that even possible?
Yes, it is possible. You like, again, within like the framework of quantum computations, there's not that many things you can do that I guess don't work out. You can even measure in the middle of a circuit depending on like if the quantum computer you're going to send your job to supports it. I suppose in that case, right, think about it, you go, this is 0, this is also 0, the control is nothing, so it's still 0 0, it's 1, boop boop, and then this is 1, and it flips that, so now it's 0 1.
Okay, so it's still like, I guess, in circuit order, everything happens.
Yeah, but again, you still have like these two distinct probabilities of 0 0 and 0 1.
Okay, thank you.
Also, very good questions, and I appreciate it. I don't think about these things all the time, so thank you for asking me to maybe consider these things. Anything else before we move on? I'm going to do some more like CTF focused quantum code.
You said these were like probabilities. So would it be like 0 probability that it would be like 0 1 or something like in this current configuration?
Yes, another very good question. Yeah, so basically, this is like a quantum physics thing. You have like a measurement rule So if you have a superposition of different possibilities, you know, like there's a probability of this happening, and it's like that squared over the probabilities of like each one happening squared. You must see like normalize something. Normalization also comes up in the challenge. So again, all the knowledge. Yeah, so and when I said like constructive and destructive interference, you can kind of think of it as like, okay, well, what are all the possibilities I can have for a combination of basic states, like, you know, 0, 0, 0, 1, 1, 0, and 1, 1, right? There's 4 possibilities. And in terms of superposition and entanglement, you notice how 2 of those combinations have like been eliminated. There's a 0% probability. And it's best to think of that conceptually, like on a real quantum computer, maybe not because it's imperfect. But conceptually, yes, because that's exactly 50-50, and that entanglement works 100% of the time. If you're interested in learning more about like what I'm saying, like, oh, like there's errors, that's something known as a mixed state, which is like a classical probability combination of a pure quantum state, where you see no errors happen. All right, awesome. So the first concept I'm going to go over, this is a bit of more like practical advice, I guess, like how to start going about a quantum challenge. So the prompt was, oh, you know, here's a quantum circuit, and you run it, and it'll print out the flag. I guess like a little bit of a advisory, kind of like what you're like. If it's a Python script, obviously you can't print out the flag. But you don't have syscalls on quantum computers, so like you can't actually print out the flag. So you do a little bit of classical post-processing. And we're given this, I call it chasm, open Q assembly, whatever. I don't know how to pronounce it. But this is just kind of a vendor independent format. It's actually very similar to regular assembly, right? Like declare your gates and you use your gates later. It's pretty readable. But most of the time, you're going to be importing that into the library of your choice, which read is Qiskit for all of you. Please do not use penny lane, and then like it's not going to work. Okay, just trust me, it's not going to work. Yeah. So when you see someone in a CTF challenge, basically like, oh, you should like run just run the quantum circuit, bro. Like generally speaking, like you just want to run it, but with some caveats. And in the case of this 7-zip file was like several megabytes, and our quantum circuit is, I think it was like 4,000 qubits, with the circuit depth, like the number of circuits in the longest path being 100,000 or something. That's not good, right? Because you're thinking, okay, 2 to the 4,000, that's pretty bad. And so in problems like these, this is where it becomes very useful to say, okay, like A, guess the paper, you know, hit up quantum computing stack exchange, or B, poke around in Qiskit to see like what functions the standard library has provided for me. And it's a little bit of both, is the answer to this question. There's actually a subset of gates known as, this is not like specific, this isn't on any of the challenges, but this is like an interesting concept. There's a subset of gates called Clifford gates, which are efficiently simulatable classically. So if your circuit only contains Clifford gates, and that includes entanglement, so Clifford gates is Hadamard, C0, and S for phase shift. Don't worry about that too much. But if that's all your gates are, and any like combination that can be made with those gates, you can simulate it efficiently classically. So that's exactly what you do. And so basically the solve here is this one line of, instead of doing AER simulator, which is like it's like the normal quantum simulator for Qiskit, you do AER stabilizer simulator. And wow, it prints out the flag. The one other thing I want to go over here, while I'm here, this first line, typically you're going to be giving a Q assembly file. At least I will be giving you Q assembly files, and most challenge authors will do that. That's how you import it and make it a quantum circuit in Qiskit. And then for the simulator, which you're going to run your code on, maybe, you have to like get a backend. This is actually, you do the exact same thing to run on a real quantum computer, by the way. You just change this string, and all of a sudden your code is being queued onto the cloud on an IBM Q device. Very cool. It's IBM Quantum. Yeah, this line of code is the thing that executes your circuit. This is also where you can do like optimization. So like you literally just like pass in like O3. I think the optimization level is actually O3. It's the same thing as you would compile it like a C program classically. And then these two lines down here, like there's really no rhyme or reason to this. Again, you're working at a lower level. Where stuff like endianness becomes important again, and you're just getting a list, like a string of ones and zeros, right? And so how you interpret those ones and zeros is like kind of important to solving the challenge. So I don't know, like I don't actually like know exactly what I'm reading here. I did write it. I didn't plagiarize it. Don't worry. But you're just like, okay, like iterate through and then like take a group of 8 bits, and that's a byte, and then you go to ASCII because it's a flag, you know. Yeah, that also wasn't very convincing, so I apologize. But these last 2 lines is pretty important for like, okay, I've like done the challenge. How do I exfiltrate my flag, my prize for all of my hard work? You can copy, that's like a good copy and paste one-liner if you want. Doesn't work all the time, but something like that will work most of the time. So you're just going to have like that, yeah.
Is 41 the length of the flag?
Yeah. Okay. So again, this is like copy and pasted from the archive CTF channel. So some of this is like generalized, but some of it isn't. Yeah, as long as you have like a binary string to int type of conversion function written, you should be good.
Have you determined that the length was 41?
Yeah, so I'm bad at like doing things right the first time. So what I'll do is I'll throw this all into a Jupyter notebook, and I'll have this res variable. And I'll like poke around, like, what's the length of res? You know, like, I'll print it, and I get a binary string. And then from there, it's like, I'm the kind of person, I will like write this line and fiddle with the numbers until I get it correct. Like, I don't actually care about, you know, as long as it's correct eventually, right? You too can become a guest god if you follow my. Any questions here?
How would you expect the circuit to tell if it has hundreds of thousands of gates?
Yeah, another very good question. So this line, this top line up here, when you import it, well, not like literally importing it, but like you're kind of importing QAssembly, which is like a foreign, it's just a vendor independent interface. You're importing it into Qiskit, and once you have it in Qiskit, it's a Python object, and you can start, you know, using all the Python methods. The most useful of which, personally, most of the time, just like get a good idea of how it works, is draw. I guess, I mean, it's like it draws out those quantum circuit diagrams we were looking at before. You can also look at the quantum assembly. It's really not that bad to read. Source, trust me, bro. But you know, like the only problem here, I did end up doing that. This one was like 4,000 qubits, and consequently, like trying to draw that, like matplotlib will crash. LaTeX probably won't crash actually, because it just spits out the LaTeX generator. Woohoo, go LaTeX. But don't do that. So you'll do text, and like I just opened it in a massive text editor. Yeah, honestly, for this challenge specifically, I was trying to do a different backend simulator, which was something called matrix state product. Don't have to worry about that, but that basically just means you can have any gates, but if there's low entanglement in my circuit, it's very easy to simulate classically. So this is why, like, in order for quantum computers to be powerful, they need both superposition and entanglement. And if you don't have one or the other, it's very easy to simulate them classically. Yeah, and again, this is like, okay, so real people actually use this stuff. So I mean, I call it phone tools. I'm kind of doing it as a service, maybe. Like this is like what actual people use to develop quantum systems and stuff, which is also why, like, if you're interested in getting this into the future, this is actually a very good introduction, because this is like what people use in the real world. And typically what you're doing is like writing a paper, you know, doing your job, and then people like me just like clown around with this stuff. Or you can write papers and clown around at the same time. That's also a very good approach. Speaking from experience. Any more questions? Great. And then we have one more challenge here. This is from Seesaw. This challenge was like, it was just okay. It was just okay. It was a mid challenge. Basically, you're getting this text output. This is your output from the quantum circuit. And in cases like this, again, earlier, you can't like literally output a string from a quantum computer. So instead, you're gonna give it like, this is like converted from a binary string, and presumably you're gonna want to like convert it back to a binary string to kind of reverse engineer. So a lot of these challenges are kind of reverse engineering, although I put them under miss because why not? But like reverse engineering mentality, I guess. For hints here, a lot of times challenge authors are going to write about like an algorithm that's named after somebody, like Shor's algorithm, or like Batanen state preparation. Like no one knows what any of these things mean. Okay, they're all made up words. Use Google. In this case, like the C naught, can not, it's a hint that you should be using C naught gates. And I think the intended solve, actually, I didn't use a quantum computer because it was like, it wasn't very exciting. Because like, as I said earlier, like C naughts are kind of like XOR. You can kind of treat them like that if you're just using them without like any quantum goodness, without any superposition. And so that's exactly what I did. Okay, good. I didn't swear. That's good. Yeah, this is not that useful, but like the main, like the lesson here I want to show you is, because again, you're like simulating everything most of the time. Sometimes you can just like classically intuit what the answer is supposed to be, and go from there. And these passive challenges have been, they give you something, you find the answer, and you submit that answer as a flag. Although a lot of challenges are, you submit something to the server does some chugging, and spits out the flag if you're right. Both of the challenges I have for you today are the latter. But these are arguably a little bit more common. Okay, we have reached kind of the end of the lecture. Here are some resources. They're actually, it's pretty good. I'm very surprised at like how good some of these resources are. DiceCTF textbook has like Jupyter notebooks online. You can use that downloading anything to go over a like very well documented and very like in really good depth amount of information. The same thing with the Xanadu quantum codebook, but in a different framework. If you want to do quantum machine learning, do that one. This is like not a well-known resource. I'm personally plugging this because I was in like a pilot program for this, and I found it really, really helpful. You go over kind of the most common quantum algorithms, like it sets you up, it goes over like the lineage stuff. It's like a very simple website, it's free. That's a personal plug. Quantum Computing Stack Exchange. Peter Shor is on Stack Exchange. I checked last night, he's not active, which is kind of sad. But yeah, people are actually very helpful on Stack Exchange. I guess that just checks out. And now we have the even better resources. This top textbook is like the authoritative source. You're really gonna need to use this in like a CTF context, but if you're interested in learning more, the second book about quantum Shannon theory came recommended to me from a professor here. I haven't read it though, but it seems very interesting. And then for guess the paper, just make sure you're going on archive. And yeah. So for next meeting, I believe next Sunday we have this Sunday we have Richard and Juniper doing Quadly. So come learn about that. We can break all the things. And next Thursday we have our social. Yay! And yeah, that's it. Yeah, so you guys can start doing the challenges, and if you need any help, just ask me and I'll try and help you out.